Average coverage can hide the group your model fails on. Mondrian Conformal prediction with MAPIE shows coverage per group and fixes intervals where it matters. You'll understand the pattern behind a pipeline that fits groupwise conformal intervals and audits subgroup coverage gaps. I'm Professor Pi, teaching AI foundations with simple Python. Models often report a single coverage number, and teams move on. That one average can hide a lot. If one demographic or one customer segment gets systematically undercovered, decisions made from those intervals will fail in the wild. Mondrian Conformal prediction is a practical fix. It conditions interval calibration on a grouping variable, so each segment meets the promised coverage. Success here looks like honest intervals per group, so downstream users can trust uncertainty estimates for the slices that matter. At a high level, Mondrian Conformal prediction keeps residual pools separated by group. Instead of a single pool that sets one interval size for everyone, we maintain per group residual sets. That prevents a noisy minority from being drowned by a calm majority. The usual trade-off is slightly wider intervals for some groups, but now those intervals are fair across slices. Picture 4 customer segments, one twice as noisy as the rest. A pooled interval will miss that noisy group repeatedly. Mondrian widens only that group's intervals, so its empirical coverage reaches the target. We will build a small regression demo that makes the gap obvious. First, we create a synthetic dataset with uneven noise per group. Then, we train a RandomForestRegressor as a base model. Next, we wrap it with MapieRegressor to see global intervals. Then, we apply Mondrian conditioning, so each group gets its own conformalization. Finally, we compare widths and coverage to quantify the fairness cost and benefit. Quick note, this code is designed to teach the core idea clearly. Library versions and local setups can vary, so check the official docs if your setup behaves differently. Now, we create the toy data to make the coverage gap visible. This snippet builds a synthetic regression dataset with uneven per-group noise using numpy. Hidden heteroscedasticity often sinks conformal coverage, so group labels deliberately receives larger variance at higher indices to make the eventual fairness gap visible. Both features come from RNG.normal draws and stack into X, while the target Y keeps a linear signal so that any coverage shortfall later is tied to the noise, not model misspecification. The seed on RNG keeps future splits deterministic, and the printed counts verify we have 200 reusable rows across 4 distinct groups before touching MAPIE. The output confirms the dataset scale is ready for the later calibration steps. That data shows the problem. Next, we train a baseline while keeping group membership aligned across splits, so no group disappears during calibration. This example orchestrates a stratified split and trains a RandomForestRegressor baseline for later MAPIE calibration. When teams skip stratified splits, minority groups can vanish from calibration. So, train test split returns aligned feature, target, and G-star arrays that preserve every segment. Base learns only on X-train to keep calibration and evaluation honest, and the fixed seed maintains reproducibility. The quick.score call here just checks we captured signal without leaking future data, leaving calibration error untouched for later steps. The output confirms the baseline forest fits the training slice with high explanatory power. With a trained base model, we can get conformal intervals the usual way and inspect per group hits. That will show how much the pooled approach misses the noisy slice. This code wraps the fitted forest with MapieRegressor to produce base conformal intervals and inspect group coverage. Focusing only on global averages hides trouble. So MAPIE global.predict builds 90% intervals, and within global tracks whether each y-test lands inside. Coverage DF and group cov summarize coverage per group, and worst group flags the segment most at risk. If you decrease alpha below 0.1, the intervals widen, and every group's mean tends to move upward, at the cost of longer sets. The output confirms which group currently suffers the poorest coverage. Seeing that gap, the fix is to condition on group. Mondrian will compute calibration statistics per group, so each slice is respected even with different noise. This snippet plugs Mondrian CP around the calibrated estimator, so every group is conformalized separately. Undercoverage often stems from pooled residuals, so Mondrian Fit ingests gcal and the loop computes coverage per partition from the returned y-interval mond. Each iteration recomputes booleans on the group slice, rather than reusing global stats, making the diagnostic trustworthy for practitioners guarding fairness. Higher alpha would shrink intervals, but Mondrian would still honor the conditioning groups while letting more misses through. The output confirms the worst-case group coverage after Mondrian stays high enough to trust. Now we quantify the trade-offs. Wider intervals buy fairness. We need simple metrics to present to stakeholders. This example compares the stored baseline metrics against the Mondrian results to quantify the fairness trade-off. Width global and width mond expose how much extra interval length is needed once groups are separated, while improvement measures coverage gains against the earlier group cov. Mean width ratio compresses that width cost into a single scalar, so you can weigh stakeholder tolerances in interviews or project reviews. Because the same test slices feed both measurements, practitioners can argue from identical evaluation points, rather than dueling datasets. The output confirms how much the weakest group gained, and how much wider the Mondrian intervals became. If you map this toy demo to a production flow, keep the same evaluation slices when you compare methods. Use the identical holdout for both pooled and Mondrian comparisons, so procurement and compliance can see apples to apples. In a large system, you will compute these same metrics per important dimension, like region, device, or cohort. Recap. What it is. Mondrian Conformal Prediction is conditional conformal calibration that enforces coverage per group. When to use it. Use it when a model's average uncertainty masks systematic undercoverage for important segments. One caveat. Per group conditioning usually increases interval width, so you trade tightness for reliability. Next step. Tune the alpha you use for conformalization and observe how coverage and mean width ratio change. Then pick the smallest alpha that meets stakeholder coverage targets. If AI Foundations in Python help, subscribe and watch the AI Foundations videos.